Here we go. Let's do this. So, quick review. Last day we started talking about functions. And so functions are, what we use in math. We've talked about expressions and equations, and now we're just introducing that function notation. And so we used function notation f of x, right? And as long as we remember that f of x is essentially equal to y, right? That's going to be really helpful when we're trying to graph stuff, for examples, but also in terms of an output, right? Y is typically our output, especially if we're talking on a graph, and so f of x is our output. So we talked about function notation. How do we use function notation? Of course, we're going to keep using function notation today, so I'm not going to go any more into it. But then we talked about, I'm just flipping through the notes here, we talked about the net change, which is also going to come back today. I'm going to scoot this way down here so I'm not leaning on it all the time. Net change is f of b minus f of a. So we talked about the net change of a function from a to b, right? But we take the end point on the rightmost side minus the endpoint on the leftmost side, and then the change between those two values, those two outputs, is the net change. And we're going to incorporate that today into the average change, or the average rate of change, but it all kind of stays the same. So the net change, we also talked about the difference quotient, which is going to kind of come back a little bit today, but we talked about the domain, the domain of a function is basically the possible values of x, right? So possible inputs, which are just your x values. And we also talked about the range. So we had talked about the domain before in section 1.4, and then we just kind of said, okay, well, we can't divide by 0 and we can't take the square root of a negative number, right? And then we need to kind of work with those two criterion and to figure out which possible inputs we have. The range, right? The range is all the possible outputs, or the possible values of f of x. So possible outputs, which we can think of as f of x, or r f of x. Then we talked about graphing functions, right? We did, before we graphed some straight lines, and we're going to graph a couple or one or two straight lines today. But in general, we're going to use Desmos to graph functions. So using Desmos, I should say, maybe. Using Desmos to graph functions. We said that, okay, there's that table which you'll want to have handy in here. Where is it? It's that table of all the general graphs, this one here, right? So I said, well, you'll need to be able to keep track of what a linear function is going to look like, what a power function is going to look like, and what a root function is going to look like. These lower three are kind of, they're important, but not as important. And so these top three, I told you that you should remember or even memorize if you can, but just the general shapes, and they're going to come into play later today as well when we do transformations. So we talked about knowing the general shape of some common graphs or common functions. Is kind of, we talked about, well, what does an even power of x look like? In general, it looks like this. It's got a parabolic shape. An odd power of x is going to look like this, kind of dancing around, right? And then the root functions are kind of off to the side, depending on the domain. So what else did we talk about? The vertical line test, right? By definition, we said that a function is something that takes one input and only gives one possible output. And so graphically what that looks like is, okay, so if you've got sort of a curve here, and if you look at each value of x, you should only have one possible output, meaning that an imaginary vertical line is only going to cross that graph once at each value of x, right? That's what makes it a function. So determining whether a graph represents a function using the vertical line test. Okay. So there are graphs that don't represent functions, and that's okay, but we're just talking about what are functions, what do we, what can we do with them, that kind of thing. And I think, oh yeah, and then finally we talked about solving equations and inequalities graphically, and that's kind of where we ended off last day. So I'll put that here. Solving equations and inequalities graphically. And I just kind of copied and pasted this chunk from last day because we said continue next day. Well, that's from last day, so I'm gonna continue today. Whee. Okay, so we were working on this problem 29, and we're given, it's really small here, but 16x to the 3 plus 16x squared is equal to x plus 1. And then we're going to also look at where is it greater than or equal to x plus 1. So what's really handy about Desmos is you can graph each of these. So you treat this as one function, treat this as another function, and where they're equal to each other is where they intersect, right? And then we can also look at where are things, where is one graph larger than the other graph, keeping in mind that we're talking about the outputs. The outputs of this graph, where are they larger than the outputs of this graph? So here, right, if we talk about that first function, 16x to the 3 plus 16x squared, well, that's going to be our purple graph here, right? So that's our first function. And I took a screenshot from Desmos just so we can draw on it if we want to and stuff like that. But I also clicked these points so that it'll tell me where these things are. The graph of x plus 1, we should be recognizing a linear equation by now, right? So x plus 1 is a linear equation, so it makes sense that we're seeing this straight line. Even x to the power of 3, even though there's this x to the power of 2 in here, right? Our highest power is x to the power of 3. So ignoring kind of what happens in the middle, knowing that the highest power is x to the power of 3, I know my end behavior is going to be something like this. And that's what I'm seeing here is I'm seeing this kind of down and up behavior, right? This x to the power of 2 is what's kind of messing with it in the middle, but in general, I'm seeing this, I know that this is kind of the behavior that I'm looking for. So it looks good. So these two functions are equal to each other at these points, right? At x equals -1, y is 0 for both of these functions. At x equals -0.25, y is 0.75 for both of these functions. At x equals 0.25, y is 1.25 for both of these functions. So that's where they're equal to each other. So I'm going to put that on here. So here, this is from today, I'll say f of x is g equal to g of x at x equals -1, -0.25, and 0.25. Okay. Next thing I want to know is, where is f of x greater than or equal to g of x? Remembering that I'm using this shorthand f of x, g of x, to kind of cut through the muck of these different functions, right? This is a pretty big function. So if I just summarize them as f of x and g of x, well, what I'm looking for is, where is this purple function? Where are the outputs higher for the purple function than they are for the black function? So if we look at these, right, if we kind of zoom in again here, for all these values of x, right, -2, for example, well, -2 has an output of -1 for the linear function, but the input of -2 is definitely, so this line just keeps going. Doesn't look like it, but they actually keep going to -infinity and positive infinity. So eventually it's going to be reaching -infinity down here. But it's going to be way less than -1, right? As we can see here. By the time we've moved over, it's going to be way less than -1. So what it looks like is from x equals -1 to x equals -0.25, that first, the purple function is larger than the straight line, right? And then from -0.25 to x equals 0.25, it's less than the straight line again, but then it switches, and all of a sudden from 0.25, so from positive 0.25 to positive infinity, it's going to be larger than the straight line. So it'll always be larger than the straight line after this point. So we're talking about f of x being greater than or equal to g of x. Well, in terms of interval notation, right, because here it's, when we're talking to where are things equal to each other, they're equal to these values, each other at these values of x. You could put the ordered pairs if you wanted. Depends on how the WebAssign wants your answers, but for these, right, as soon as we have inequalities, we're typically talking about interval notation, right? And so on the interval from x equals -1 to x equals -0.25, f of x is greater than g of x. So from -1 to -0.25, notice that I want f of x is greater than or equal to g of x. So what I should be using is square brackets around these two, right? Because it's going up to and including those points. So I'm going to change that. From -1 to -0.25, union, right? Because then it takes a break and is less than the straight line, and then it picks it right back up at positive 0.25. And again, it's including 0.25, so square bracket 0.25 up to positive infinity. Infinity is not a number, so we always put a round bracket around infinity, or positive or negative infinity. Okay, great. So it's kind of the end from last day, right? Wrapping up last day. All right, so if I asked you to look at this graph and tell me where it's increasing and decreasing, you would probably have a pretty good intuitive idea of where it's increasing. So here it looks like it's increasing, and then at this point it stops and it starts decreasing, and then it starts increasing once more, right? So of course here this straight line is just increasing, 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 so that's not very interesting. But for any sort of curve, right, then it's going to be increasing until it reaches a point, and then it'll start decreasing again, and then increasing, and we get this kind of wavy structure. So you probably have a pretty good idea of when a function is increasing and decreasing. So what I mean by saying that is trust your instincts. You know when a function is increasing or decreasing. If I give you a graph, you can tell me where it's increasing, where it's decreasing, right? So some of this stuff you already know, and that's what I want to highlight, right? And so you probably have a pretty good idea of when a function is increasing or decreasing, right? So if we have something like this, so my x-axis and my y-axis, if I've got something that looks like this, up until this point it's increasing, and then it switches to decreasing. Whee! And then it goes back to increasing again. Okay. But we can also consider just the mathematical kind of theorem of increasing and decreasing. So, but we could express this idea mathematically. Which might not come to you as intuitively, but I just want you to, oh, wrong functions, part one. But I just want you to be okay with, okay, I know what it means to be increasing and decreasing, so let's start there, and then let's talk about the definition of increasing and decreasing. Well, here, if we're talking about some value x1 and x2, it looks like x1 is less than x2. In fact, it's part of the definition. Well, if x1 is less than x2 and f of x1 is less than f of x2, right? The output at x1 is less than the output at x2. Well, then I must have increased to get there, right? Same idea. If x1 and x1 is less than x2, if the output at x1 is larger than the output at x2, then I must have a decreasing function, right? So we know what these things look like, increasing, decreasing, but it's going to be really important that we can start to incorporate and start to read stuff like this and say, oh yeah, that makes sense because of what I know increasing and decreasing look like. Okay. So we already know what these things look like, but we can prove it mathematically using the statement. Where increasing and decreasing kind of lead us to are, we didn't talk about it here, but if we're increasing and then all of a sudden we switch to a decreasing function, right, or a decreasing part, then what happened here must be a maximum. Right, and same thing here, if we're switching from decreasing to increasing, at that point, we must have a minimum, right? And so we use this to figure out where we have maximums and minimums. So a maximum, we're gonna call them local maximums and local minimums. The local part of it is just saying, hey, I don't know what happens at the, other points of this function. I just know that what I'm looking at is a maximum for the section that I'm looking at. And I'll show you an example, but we just kind of guard ourselves by saying local maximum and local minimums. So a maximum or a local maximum happens at the point where a graph, and I'll say switches, right? It's not really a mathematical term, switching, but switches from increasing to decreasing, right? And vice versa for local minimums. And vice versa for local minimums. Minimums. Right, so if you've got something that looks like this, right, let's put a little whoop. Yeah. My graphs always kind of look the same. Right here, we're increasing. And here we're increasing. And then we said here we're decreasing. Well then, let's see. At this point here, this must be a local max. And this point here must be a local minimum. Okay. Okay. Just like I was saying before, right? A lot of this stuff, if I just gave you the default graph that I started with, and I asked you to point out the maximum and the minimum, you would probably tell me the maximum is here and the minimum is here, right? You don't need to think about, okay, where is it increasing and then where is it decreasing, right? But that is what's happening. Right, so even though we understand, you know, increasing, decreasing, maximum, minimums, this is actually what's going on behind the scenes, right? It switches from an increasing function to a decreasing function. So I'm gonna go grab the little blip on maximums and minimums. So we call them local maximums. We can have multiple local maximums and minimums, okay? One thing that I want you to remember is that it's just kind of assumed that these graphs always kind of continue in the direction that they ended, right? So this one would keep going up and up and up to positive infinity. This one would keep going down and down and down to negative infinity. Right, so even if the graph ends here, the function itself doesn't necessarily end there. So the reason that we say local maximum is because even though this point is higher than this point, if this keeps going over and over and over, right, then pretty soon, right, pretty quick after here, it's going to be higher than this maximum. So that's why we call them local maximums, because they're the maximums that we can see, right? The kind of dips that we can see. Same thing with the minimums. This minimum is higher than this minimum, but pretty quick here, we're going to reach a new minimum, right? But we call these local max and mins just because they're the ones that we're looking at right now. And we call them local because we understand that there are points that are larger or smaller on this function, right, that we're not talking about. So what does it mean? So f of a, so a function f of a is a local maximum if f of a is larger than all other f of x when x is near a. So what does that look like? It looks like here at a, right? F of A, so the output at A is larger than all other outputs around X equals A, right? So it's going to be the largest out of all these possible outputs hanging out around A. Same thing for the negative, right? So I'm actually going to delete this or remove this here because we use A again for the minimum, and so that could get confusing. So I'm just going to remove this here and kind of shift it over here to talk about the minimum. Well, if it's a minimum, technically what's happening is that the output at A is going to be the smallest out of all the other outputs hanging out around X equals A, right? So we know what these things, the local max and mins, look like, right? And so if I give you a graph like this one, let's just do, I'm just going to copy in the first two, leave the other two. We'll just do the first one actually, because it's pretty basic. So here, we're going to do 43. And so it says that the graph of a function f is given, and then we're going to use the graph to estimate the following: all the local maximum and minimum values of the function, and the value of x at which each occurs, right? So we need to figure out what value of x makes this happen. The intervals on which the function is increasing and on which the function is decreasing. So just looking here, we can tell, okay, it's decreasing, increasing, decreasing, increasing, right? And this is basically the opposite. What I want you to remember, right, is that these things are going up and up and up and up, and this one is going down and down and down, right? So even though we're only looking at a certain part of the graph, right, we're kind of zoomed in, know that this thing extends beyond the graph. Okay, so here, the local max, let's start with the local maximum values. Well, it looks like the local maximum value is really here, right? I don't see any other local maximums. Yeah, these are higher, right? But they're not local maximums. They're just kind of taking off. And so, but I do have two minimum values. So I'll use a different color here. We'll start with this maximum. Looks like at x equals 0, y equals 2, looks, because they've shown us that the scale is just 1 unit per square. And so here, this is at 0, 2. So the maximum happens when x is 0 and the maximum value is 2. Okay? So let's talk about the minimums. Here, this minimum value is when x is -1, -2, and y is -1. So here, this is at -2, -1. And then doing the same thing for this value when x is +2, y is 0. Okay. We want to know the interval where the function is increasing. So for 43, it's increasing. And I'm going to use interval notation again, right? I'll use pink for increasing. So here it's decreasing, here it's increasing, then it's decreasing, and then here it's increasing. So it's increasing. I'm not going to include the max and mins here in my interval, and the reason for that is because it's not doing anything at that point. That's where it switches, so that's why I'm excluding them. If you wanted to include them, I'm sure it's fine, but technically they're not included. So it's increasing from x equals -2 to 0. -2 to 0, but then it picks back up from x equals 2 to +infinity. Of course, it's going to be decreasing on the opposite interval. I find that very hard to deal with, so I find it easier to just look here and say, okay, well, it's decreasing from negative infinity to negative 2, and then from 0 to positive 2. And then it's decreasing, which I'll use green for, which here and here. So the interval that it's decreasing at is negative infinity to negative 2, picking back up at from 0 to 2. Good. Maximums and minimums are really important, especially if you're, talking about money stuff, right? If I tell you, okay, here's your function, here's your profit function. Well, you want your profit up here, right? So we need to be able to figure out, well, what, how many hours do I need to work to be able to get this sort of profit, or how many units do I need to sell to have this highest profit? Or even if that's not possible, maybe I want to maximize here to this local maximum here. So another way that we could think about it economically is if you want to minimize the cost, well, then you want your cost to be down here if this is your cost function. And there are a lot of different things. So in general, finding maximums and minimums is called optimization in math, and it's a huge field. And we can optimize all kinds of things. We can optimize populations, we can optimize kind of speeds, costs, of course, profit functions, so economics, anything that you can kind of maximize or minimize is optimization. And so that's why we need to know about these local max and mins and how to identify them. But they're really not that bad, right? We know intuitively what they are. Good. So the next section that we're going to dive into is section 2.4, which is the average rate of change. Now 2.4 is basically just building off of that net change that we already talked about, f of b minus f of a. But now we're talking about the average rate of change. So it's a really quick section. There's nothing really going on here. There's only one concept that we need to take out of it, and it's the average rate of change. So, which is the name of the section? Average rate of change. Oops, it's not. So, I'm gonna steal this little guy, I think. So the average rate of change of a function f of x between x equals a and x equals b is the change in y, which is really what we've been calling the net change, f of b minus f of a, over the change in x, right? So if it changes this much on the y scale, how much did it change on the x scale? And that's your average rate of change. So here, notice that this here, this is the net change f of b minus f of a. All right. So nothing really changes. They're throwing in the word secant line. The secant line, we haven't talked about it, and we don't really need it until calculus or need to know what it is, but it's not that bad. It's the secant line, if you've got a curve and you've got 2 points on that curve, the secant line is just the line that connects those two, just straight across. Doesn't care where the graph is going, it's just connecting those two. So the secant line is really just f of b minus f of a, and then divided by b minus a, or the slope of the secant line. That's what I meant to say. So we're going to talk about, well, we can find the net change, or we can find the average rate of change. Typically, it's easiest if you start by finding the net change and then find the average rate of change, because then you'll have this chunk done already, right? And then you can just divide it by b minus a. So let's do some examples here. Okay, let's see if I can pick a good one here. Let's do 13 because it's dealing with a fraction in there, and so just kind of keeping on top of these fractions that you had to do for test 1. So 13 says h of t is negative t plus 3 over 2. First thing I want to highlight here is that, okay, well, we're using t as our input, but if you want to, you can think of them as x's. And h of t is our function or our output. H is the name of the function, t is the input, so this is essentially your y, right? One thing I want you to look at and think about is this is a linear function, right? The highest power of x is 1, so this is basically y equals mx plus b, right? This is a linear function with a slope of -1. Notice that this is a linear function with a slope of -1. Nothing more, nothing less. So it's good to be able to recognize these functions, right? And kind of the core functions. So if we just browse through here, right? 3x minus 2 looks like a linear function to me. 3 minus 1 over 3t looks like a linear function, right? Same thing here, linear function, linear function. Here you've got a a quadratic. The highest power of t is 2, and then another t here. And so now we've got this parabolic shape. So that's what I mean by, okay, we need to know what these things look like. T squared, that's our highest power of t, so we know it's gonna overall look like a parabola. Here we've got z squared, same thing. Overall, it's gonna have this parabolic shape. X to the power of 3, all of a sudden, power of 3 is our highest power, so now overall it's going to have this this kind of end behavior. The minus 4x squared is going to make things weird in the middle, but in general the end behavior is going to be looking like x to the power of 3. T to the power of 4, same thing, we're back to a parabola, right? And so just knowing the general shape of these things is really useful. And especially if you keep track of, okay, do I have a linear function? Then they're just easier to deal with, right? So what we can do is determine the net change and the average rate of change between the given values of the variable. So what we have to do is we have to find the net change between t equals -4 and t equals 1. So part A, the net change is f of b minus f of a, right? Here, our function isn't called f, it's called h, but that's all right. And our a is -4 and our b is 1. So what I get is, in our case, it's h of 1 minus h of -4. F of b minus f of a translates to, and if you find it helpful, you can always just say here that this means that a equals -4 and b equals 1, right? You can always just make a little note to yourself. Okay, a is the first one, b is the second one, and then I want to kind of reverse these So now we're back to using function notation, right? H of 1 is, I take this function h, negative t plus 3 over 2, and I plug in 1 wherever I see a t. Same thing here, but I plug in negative 4 wherever I see a t. So I'm going to treat these as 2 chunks, but I am going to have them on the same line, right? You're more than welcome to figure out h of 1 first, h of negative 4, and then subtract them later, but don't forget to subtract them. But I'm going to do both of them on the same line, but I'm going to separate them with big square brackets just so I can visually see that they're 2 things. So I've got negative 1 plus 3 over 2 minus negative 4 plus 3 over 2. So now all I need to do is start to simplify these things. We've worked a lot with fractions already, right? We're going to keep working with fractions. Fractions are going to haunt us throughout this whole thing. And so I have negative 1 plus 3 over 2. I need to get a common denominator before I can combine these, right? Ultimately, this is just a number. So I need to combine these to have a common denominator. Same thing with here, negative 4 is 4 plus 3 over 2, so I need to have a common denominator of 2. So I get, I'll put big brackets, negative 1 times 2 over 2 plus 3 over 2 minus 4 times 2 over 2, right? Just forcing that common denominator by multiplying by 1, right? So I get negative 2 plus 3 divided by 2. So I'm combining the numerator and the common denominator immediately, moving a little bit faster than we're used to. 8 plus 3 over 2. What's nice about this is, again, now I'm subtracting 2 fractions, but they already have a common denominator. And so that's a little bit of work saved. So what I'm going to do is negative 2 plus 3 is 1 over 2. I'll ditch these brackets now. I don't really need them. Making sure that this minus translates, so minus 8 plus 3 is 11 over 2, which puts me at 1 minus 11, negative 10 divided by 2, which would simplify to negative 5, right? So my net change is negative 5, which means I've dropped down from negative 5. Makes sense, right? Because we know that this is a linear function with a slope of negative 1, so we are expecting it to have this decreasing change. And so it all checks out so far. So now it's time to do the average rate of change. The average rate of change is f of b, minus f of a divided by b minus a. And I know f of b minus f of a, which is really h of 1 minus h of negative 4. So I'm going to rewrite it in terms of this function. So this is h of 1 minus h of negative 4 divided by b in this case is 1 and a is negative 4. 1 minus negative 4. Sorry. Throat got so dry. All these functions. So we know what h of 1 minus h of negative 4 is. We just found it to be 5, or sorry, negative 5. So negative 5 divided by 1 minus negative 4 is actually just 1 plus 4, which is 5. So my average rate of change is negative 1, right? Which is different from the net change, right? Because it's incorporating, well, how wide of a spread did you look at, right? Over this spread, the average rate of change is -1 per increase in X. Let's do one that's a little bit more. Let's do 20. The reason I picked 20 is because I've got this X equals 2 plus H. So we've got this kind of generic movement from X equals 2 to 2 plus H. All I've moved is H units. I don't know how many that is, and it doesn't actually matter. We saw something like this when we were dealing with difference quotients last day. It doesn't, you don't have to remember that, but that's where things come from. So, because I won't remember any of this, I'm gonna copy and paste it down here. Okay, so I've got my function y minus 3x, or 1 minus 3x squared, and x is 2 and x equals 2 plus h, right? And so here, my a is 2 and my b is 2 plus h. My net change here is going to be this function evaluated at 2 plus h minus this function evaluated at 2. So part A, the net change is f of b minus f of a, right? Where x equals 2 plus h is my b and x equals 2 is my a. So that's the same as f at 2 plus h minus f at 2. F is the name of my function, so that's why I'm keeping it. And now, same thing that I just did, right? I'm going to plug in 2 plus h into this function and just deal with them individually. And then I'm going to subtract plugging 2 into this function. So this is going to be 1 minus 3 times 2 plus h squared minus, and then again with plugging in 2, 1 minus 3 times 2 squared. Remembering that 2 plus h squared is 2 plus h times 2 plus h, right? So I don't want to see this 2 expanded in there. That's bad, illegal math. So 2 plus h squared, I'm going to need to expand that before I can simplify this. And so what I get is 1 minus 3 times 2 plus h times 2 plus h. I'm going to move this over just a little bit, just a smidge. Minus 1 minus 3 times 4. You could probably do this in one go because it's just a number, but because I've got time, because I have to simplify on this side anyways, I'm just going to take my time working through it. So I get, first I'm going to have to expand this 2 plus h times 2 plus h. And if you're feeling really confident in your expansion, then you could go and simplify it immediately. I always write out all the terms. So just to be careful, 2 times 2 is 4 plus 2h plus 2h plus h squared minus 1 minus 12. So here, right, what I mean is some of you might go, well, there's only 2 of you here. You might go to 4 plus 4h plus h squared immediately, and that's totally fine. I just always write them out so I don't forget anything. Right? I'm just highlighting that this should be 1 minus 12. So I get 1 minus 3 times 4 plus 4h plus h squared minus -11 . 1 minus 3 times 4 plus 4h plus h squared minus -11 So now I get, and I could probably get rid of these big square brackets soon. They're just kind of helping me visualize where this function stops. So 1 minus, and what I'm going to do is I'm going to bring in the positive 3 inside, and then I'm going to bring in the negative. You could definitely bring in the negative 3, but it can get tricky that way. So I always bring in the 3 and then bring in the negative afterwards. So 3 times 4 is 12, plus 3 times 4h is 12h plus 3h squared, and then plus 12 on the end. Sorry, I don't know where I got 12 from. So minus negative 11 is plus 11. Okay, now I'm ready to bring this negative onto the negative. So 1 minus 12 minus 12h minus 3h squared plus 11, right? I've got 1 minus 12, that's negative 11. Negative 11, and then minus 12h minus 3h squared plus 11. Well, of course, these are going to cancel. Negative 11 plus 11. So all I'm left with here is negative 12h minus 3h squared. You don't have to, but it looks like I can factor out a negative 3h. So I'm going to do that. Negative 3h times 4h plus h. Not 4h. Negative 3h times 4 is negative 12h. Good. Negative, so it's 4 plus h. Yeah. I'm just going to quickly expand that in my mind. Negative 3h, negative 12h minus 3h squared. If you stopped here, that's totally fine, right? But here, it's a little bit easier to look at. Okay. So that was quite a bit of work, right, for the net change. But now we can use that to find the average rate of change. So then B, the average rate of change, is f of B minus f of A divided by B minus A. Okay, so we just found that f of B minus f of A is the same as f of 2 plus h minus f of 2. So I'm going to rewrite it that way, which is f of 2 plus h minus f of 2 divided by B minus A. B in this case is 2 plus h minus A, which is 2. So what I get, right, if I kind of expand this and simplify this, I get negative 3h times 4 plus h, replacing that numerator with what we just found, divided by 2 plus h minus 2. Well, 2 minus 2 is going to go away. So I have negative 3h times 4 plus h divided by h. What's nice is that I've already factored out this h, and because it's only multiplying up top here, I'm allowed to cancel it with this h on the bottom. So, dink, dink. This becomes negative 3 times 4 plus h. Nice. Good. So, in the next section is on linear functions, and we've actually, we've spent some time on linear functions already in section 110. We talked about, you know, the slope-intercept form. We talked about, well, we talked a lot about linear functions. So just remembering that linear function is anything that you could rewrite as y equals mx plus b, right? Or f of x is ax plus b. And the slope is a and the y-intercept is b, just as a reminder. Well, the only thing that's kind of new that we're introducing here is that the slope of a linear function is going to be the same as the rate of change of that linear function. And so that's the only thing that's kind of new here that we're introducing. Usually I start on a fresh page, but it's such a big jump that I'm going to do 2.5 linear functions. So here, right, the slope of a linear function is the rate of change of that function. So what I want to do is I want to jump back to the first example that we did here, where we said, okay, well, I've got a linear function here with a slope of -1. So what this thing is saying is that my rate of change, my average rate of change, should be -1, which it is, right? So all it's saying is that if you have a linear function, the slope is that rate of change, which makes sense. If you've got this straight line, then the average rate of change is also going to be the slope. So if we have a linear function, we know the slope is also going to be the rate of change. We'll do one example here, but nothing too crazy. Let's do one of these. Let's do 24. The only reason I chose 24 is because it's got this kind of capital A of R, which isn't really notation that we're used to seeing, but it is function notation, and it is a linear function because we've just got this one R with a power of 1. So we could think of this as y equals mx plus b. Right? So in 24, right, we've got this linear function, a of r equals -2/3 r minus 1. The question tells us to sketch the graph. Sure, let's do it just for some practice in sketching the graph, but of course we're going to use Desmos to check our work anyways. So if you wanted to just use Desmos, that's totally fine. But then we have to find the slope of the graph, and we have to find the rate of change of the function. Well, we already know parts B and C just from here and what we just established up here. Well, the slope is -2/3. So the slope is -2/3, so the rate of change is -2/3, right? So we're going to focus on just a quick sketch of this thing. Remembering that our input is now called R and our output is called A of R, but it still behaves the same way. So remember how we sketch a graph of a linear function? We just pick two values of R or inputs that are convenient, evaluate and find the output, and then we'll have these two coordinate pairs that we can graph and then draw the line and extend it. So what I'm going to do is I'm going to make a table of values here. So I've got R. I'm trying to keep it on this page, so we'll see how that goes. But R is oops, negative 2 over 3 r minus 1. So of course I'm going to pick convenient values of r. I'm going to start with r equals 0. That's my go-to, right? Because it's going to make this whole mess go away. And so if I plug in r equals 0, then a of r equals negative 1, right? So what I've got in terms of an xy coordinate, I'm going to use different colors so I can show them here. I'm at 0, negative 1. Then I still want to keep picking convenient values of r. Usually I would pick 1, right? But r of 1 is actually harder to deal with because then I have negative 2 over 3 minus 1. So I'd have to find the common denominator, I'd have to combine them, and it just makes it harder. And I might end up with a nasty fraction. Instead, I'm going to pick a multiple of 3 because that's going to cancel with this 3. In fact, I'm just going to use 3 because that's the easiest. So here, if I use 3, then a of r is going to be negative 2 over 3 times 3, and then minus 1. Well, 3 over 3 cancels. Negative 2 minus 1 is negative 3. So now at this point here, I'm at 3, negative 3. So when I'm sketching this, I need to keep track of, I need to figure out what my axes are. On my x-axis, the points that I've found go from 0 to 3. So I need to have at least 3 units on the x-axis to show my graph. And then on the y-axis, I need to be able to go from at least negative 1 to negative 3. So I've got these kind of clever stickies here. Can I make it work? I just need one more line, so I'm going to scoop this all up here. Everything. Whee! Make myself some room. Ta-da! Like nothing happened. Great. So I'm going to keep in mind my values of x and y here when I draw my grid. So what it's going to look like, I'll put my x-axis up here. So now I'm going to draw my first point, which is at 0, negative 1. In fact, I'll put 1, 2, 3, 4, negative 1, negative 2, negative 3. Okay. So in light blue, I'm at 0, negative 1. So when x is 0, y is negative 1. And then for my green point, I'm at 3, negative 3. So when x is 3, y is negative 3. Right? So this is how we're going to draw graphs. Now, I connect these. I just take some sort of straight edge, and I connect these, and then I draw the line. And then I don't want it going over to the next page. So I'm just going to erase this little section here, I think. Okay. So we can confirm this using Desmos, right? If we graph negative 2 over 3 r minus 1 using x instead of r, if we go to Desmos, then we can graph negative 2 divided by 3 times x, and then, shoot, what was it? Minus, no, I've lost it, minus 1. There. So it actually already tells us that the y-intercept is negative 1, which we knew, right? And then the other point that we found was at x equals 3. trying to land on it there. When x is 3, y is -3, and I can't seem to capture it there. Just briefly. Another thing that you could do if you wanted to, you could put a line at y equals 3, or sorry, -3. And then just confirm that it's at 3, -3, right? So we've drawn the same line. So that's good. And then the slope, we already know is -2/3. And the rate of change, we know by the properties of a linear graph that the rate of change is the slope. And so the rate of change is also -2/3. Makes sense that we've got this downward slope because we've got a negative slope, right? So we should have a negative graph. Nice. Okay, so this, let's see here. Oops, I went to the wrong one again. So that's kind of the end of functions part 1, but what I want to do is I want to get into functions part 2, and I'll readjust them and repost them after today. And so we're going to do 2.6 as well today because we got to kind of get through this stuff. 2.6 is a little bit, it's okay. It's just a lot of stuff to have kind of available to us. So we're talking about transformations of functions. So transformations of functions, essentially we start at some base function, x squared, for example, and then we can manipulate that graph to move it up, move it down. We can flip it. We can move it this left. We can move it right. We can move it. We can stretch it. We can shrink it. We can amplify it. We can do the opposite of amplify it. So we can do all these things with this graph, and we can do a combination of things. But in order to do that, we need to know all these rules. So we're going to talk about all these rules, and what you'll see if you scroll through 2.6 on your own is there's a lot of little blue kind of info blurbs, right? And so we're going to talk about each of these, and then we're going to just talk about some general examples, and then that'll be good. So after the even and odd functions, then there's just exercises. And in fact, you'll be happy to know that I labeled these as optional. Not really going to do any of these because I'm not going to watch you graph stuff by hand, but they're good to know still. So, and then same with these. These are just kind of good for practice again. But we're just going to talk about each of these little blurbs and then do a couple of examples, and then that'll be it for 2.6. So for section 2.6, 2.6 is called transformations of functions. So before we dive in here, there are just two main things that we need to remember, and then there's other things, but two main things that we need to remember. If we're doing something to f of x itself, so f of x as a unit, we're manipulating the y values, right? If you think about y equals f of x, then you're manipulating the y values. So there might be a stretch, or there might be a shift up or a shift down, right? So if you're manipulating f of x, things are happening vertically, right? if you're manipulating the x inside the f of x, then you're going to be manipulating things horizontally, right? So that could be horizontal shifts or horizontal kind of expansions or contractions. And so just remembering those differences is going to make a big difference. Changes on x, at least for me, don't behave the way that I expect them to. They typically do the opposite of what I would expect them to do. We'll see. So in general, a transformation can be done vertically, right? So up, down, or horizontally, which is kind of left, right. Okay. If the function is being manipulated or transformed on the whole f of x, so if f of x is being manipulated, the transformation will be vertical. Okay. Whereas if the x inside the f of x is the one being manipulated, then we're going to have this horizontal shift. So if the x inside f of x is being manipulated, the transformation will be horizontal. One thing to note here, at least for me, right, note manipulations on x are often counterintuitive to what we think they are going to do. On x are often counterintuitive to what we think they will do. Making them counterintuitive, I guess. Whatever. So let's have a look at some of these. I think, did I grab it already? Yeah. So here, if we're talking about vertical shifts, right? This is behaving the way I assume it will, right? So we're just establishing that c is going to be greater than 0. If it was less than 0, then something like f of x plus c. If it was negative, it would actually be f of x minus c. So it's just establishing that c is behaving the way you think it will. So to graph y equals f of x plus c, what you're doing is you're taking the original graph, which is this blue graph, and everything is just moving up by plus c, right? So up by c units. And then same thing, if you have f of x minus c, then it's moving, everything is moving down, but nothing's shrinking or anything like that. It's just moving down by c units. So every value is moving down by c units. So here, notice that f of x plus c, the plus c is on the entire f of x, as opposed to, let's see if I can grab this other one. There you give up. Okay. Keep it there, I guess. So here, what I want you to notice for this previous one, c is added or subtracted to all of f of x. C is added or subtracted to all of f of x. Right? The difference here with horizontal shifts is, again, we're establishing that c has to be positive, otherwise it makes things messy. But if we have a graph of y equals f of x minus c, so now I'm subtracting c from each x, well, although I would so for me, intuitively, if I'm subtracting c, then I would want to move it to the left c units, but it actually moves it to the right c units. So this is the part that I find counterintuitive. Same thing with f of x plus c on the x actually shifts it to the left c units. So you have to keep track of that, right? But as long as you have these little blurbs handy, then you're fine, right? And so you want to shift the graph to the left c units. It actually behaves kind of differently. So here we're going to notice that c is added or subtracted to x inside f of x, right? So it's the x that's being manipulated, and just remember that, at least for me, it moves the opposite way that you want it to, right? I actually find that helpful if I remind myself, oh, it does the opposite of what I think it's going to do, then I find it helpful. So we can do things like, we can combine these, right? If we have a look at this graph here, we can combine these manipulations, right? But we have to start with some core graph. And that's what I mean. It's really helpful to remember all those core graphs that we discussed last day, right? The linear function is not that interesting, but it's on the list. The power functions, the root functions. Here we've got a root function and we've got the square root. So we should know what the square root function looks like. Then we could look at the square root of x minus 3. Well, from x, I'm subtracting 3, which actually moves everything just over to the right by 3 units. Okay. And then what I could do is from here, I could add 4 units to all of f of x. So plus 4, so root x minus 3, and then plus 4 just shifts everything up. Okay. Typically, if we want to draw something like this, right, this biggest function, f of x is root x minus 3 plus 4, what we do is we start with the most simple version of the function, root x, and then we slowly build out. So we kind of bloom out. So we subtract 3 from x, which moves it over by 3, and then we can add 4 to that function, moving it up by 4 units. To graph something like f of x equals the root of x minus 3 plus 4, we start by using the simplest version of the function. So the simplest version of the function, and then apply the manipulations, I'll call them, by kind of blooming out, and then apply the manipulations by, I always like to think of it as blooming out, right? So you start at root x and then you subtract 3 from x and then you add 4 to that whole thing, right? So, and then apply the manipulations by blooming out from that basic function. Right. So for f of x equals the root of x minus 3 plus 4, the first thing you would do, right, is you would draw f of x equals the root of x. And then shift f of x equals the root of x to the right by 3 units to get f of x is the root of x minus 3. And then you would shift it up by 4 units. Then shift f of x equals the root of x minus 3 up by 4 units to get f of x is the root of x minus 3 plus 4. So you need to be able to dissect this a little bit, right, to figure out what you need to start with and then kind of where to go from there. But you should be able to do some of these transformations, right? Or, I mean, you always have Desmos to check your work, so always check your work, but these are just kind of basic transformations. Negatives are going to reflect the graph, okay? And it depends on if you're putting a negative on the f of x or if you're putting it on the x value itself. Okay. Here, if you've got y equals negative f of x, so here your f of x itself is going to be negative, which means all your outputs are going to go from positive to negative, or if they're negative, then of course the negative of a negative makes a positive. So what happens is you're revolving or you're reflecting around the x-axis, right? And so that's what you see here. If you start with y equals f of x, then y equals negative f of x is just a revolution around the x-axis, right? Because your y values change, your x values do not change, right? So here, I'll expand this a little bit. Oh. So here, the y values are negated. X values stay the same. Whereas here, if I'm talking about negative x, right? So now I'm taking all my x's and I'm making them negative. So over here, if I had positive x values, then if I take the negative of them, this is the one time that they behave the same way that I think they're going to, then I just make them negative, right? And so it's a reflection around the y-axis instead of the x-axis. So, but it's still got that kind of revolution. So if it was positive, it's going to be negative. If it was negative, it's going to become positive, right? And it's got this revolution around the y-axis instead of the x-axis. But notice that the y values, they stay the same, right? It's just the x values that are changing from positive to negative. So here, the y values stay the same, and the x values are negated. Good. So we're going to talk about all three of these other kind of properties, transformation properties, before we do an example, but then we'll be all done for this section, so that's nice. So the vertical stretching, so if it's vertical, right, remember vertical things are manipulations on f of x, right? So if you're multiplying f of x by some value c, it depends on if c is greater than 1. So if c is greater than 1, then you kind of stretch this thing out. So it amplifies it, so it makes it kind of taller. Then you multiply each value of y by c, right? Whereas if c is between 0 and 1, then you're going to shrink it down, right? So if c is 0.5, right, a half, then of course it would become shorter than it already was. So here, we're multiply each value of y by c, right? So we can amplify it, or I guess, I don't, de-amplify, no, shrink it down, minimize it. So we call it stretching if it becomes bigger, and shrinking if it kind of shrinks down and smaller. Okay. But just recognize that the c is outside the f of x. For the next one, right, we're going to talk about the horizontal shrinking and stretching. So now notice that the c is multiplying the x, right? So it's not multiplying the f of x, it's just multiplying the x. And again, it kind of does the opposite of what you think it's going to do. So if c is greater than 1, right, so a whole number or even a fraction greater than 1, then you can shrink the graph horizontally by a factor of 1 over c. That's kind of weird, right? But it's just how it is. So we just need to remember that. So notice that if the blue line is our original function, y equals f of x, then if I have y equals f of c times x, I actually smush it together horizontally, right? And so, but one thing to keep in mind is that all the y values stay the same, right? So all the potential y values, it still has that same range as it did before. It's just that the domain has been smushed together. And then if you've got a small value of c, it actually stretches it out like this, right? So if c is between 0 and 1, then we stretch it horizontally by a factor of 1 over c. So if the blue line is our original function, and then if c is small, then we get this kind of stretched out version of the graph. Okay. So here what we're doing is we're multiply each value of x by 1 over c. And that's what makes it behave the opposite of what you think it's going to do. Okay. The last thing I want to talk about, and it's not, you know, the most important thing is everything that we've talked about so far, but we should talk about even and odd functions. We've talked about them just before, right? So we can have even or odd functions. We've talked about even powers. Even powers have this parabolic shape, and odd powers have this kind of dancing shape. And so, but by definition, f is even if you're able to plug in negative x and it still looks like it's the same as f of x. And so one obvious example would be x squared is even, right? Because x squared is symmetric around the y-axis, right? F is odd if there isn't that symmetry around the y-axis, but there is some sort of symmetry around the origin. I find that that's hard to kind of think about, but as long as you remember that if you have the highest power is odd, then you have an odd function, right? And so that kind of helps, right? So for example, if you have f of x equals x squared is even, since if I'm able to show that f of negative x, which is negative x squared, which is x squared, is the same as f of x, right? So that's how you would show that things are even or odd, just using these properties. We're not going to focus too much on that. I'll leave that for calculus, right? But you do use even and odd functions in calculus, and so it's good to know that you could show it, but I'll just leave it. Okay. So some of these examples that I want to go through, I just want to go through. So these use generic functions of f of x. So we're not talking about specific functions, but later on, you can easily make the extension, especially from here, you can easily make the extension to specific graphs, and then you can check them in Desmos. But for us, let's just go through some of these and talk about, how would these transformations take place. So the ones I want to do to kind of illustrate, oh shoot, I didn't write them down, but let's start with, I don't know, maybe 11 A and B. So for 11A, we've got y equals f of x minus 5 and then plus 2. What would this look like? So we don't know what f of x is, and it doesn't matter, right? But what we're saying is, okay, if I drill down to the most basic function, that would be f of x. First thing I've done is I've subtracted 5 from x, which actually shifts it to the right by 5 units, right? So it gives me that horizontal shift. Second thing I'm doing is I'm moving everything up by 2 units. So I'm going to use different colors to kind of show that the first thing I did was move f of x to the right by 5 units. And then the second thing I've done is then move it up by 2 units. So then take that whole shift and move it up by 2 units. Move everything up by 2 units. B, well, B is very similar, so maybe I'll skip it. I'll pick another one that's kind of more interesting. Let's do 13A. 13A is y is negative f of x plus 5. So I start with my basic function, and then I do the first thing that's been applied to it. And in this case, it's been negated. So that means that all my y values, right, are going to be turned negative, right, which is a reflection in the x-axis. And you can remind yourself, where was it? Here. Y equals negative f of x, reflect the graph in the x-axis. Right, and so you're going to turn all your y values negative, is the first thing you're going to do. Make all the y values negative y, right? If you have a negative value, if you negate it, it becomes positive. So I don't want to say negative, but make all the y values negative y, which means reflect in the x-axis. Then once I've reflected, then I need to move things up by 5 units. Move everything up by 5 units. So that's a reflection in the x-axis. Let's just point out one that would have a reflection in the y-axis here, right? Negative x. But I'm not going to do that one. I want to do one that's a little bit harder. Let's look at 16a. So 16a, and then the last one I want to do later is 18a, and then we'll be done. How about that? So 16a is 1 over 3 times f of x minus 2 plus 5. Okay. So you need to figure out what f of x is, and then the first thing that you would do, right, is subtract 2 from x. Then once you've done that, then you multiply that f of x by 1 over 3, and then you're adding 5, right? So just seeing how these things kind of blossom out or bloom out is really important. If I subtract 2 from x, I'm really shifting things to the right by 2 units. So shift f of x to the right by 2 units. Right, and then maybe just so I can see the chain of events here, to make f of x minus 2. Next thing I'm going to do is I'm going to deal with this 1 over 3 times f of x minus 2. But I've already dealt with f of x minus 2, so now I'm multiplying by a constant of 1 over 3. So this is going to be a vertical stretch or shrink. And in this case, 1 over 3 is between 0 and 1. So what's going to happen is I'm going to shrink this graph vertically by a factor of c, right? So I'm going to decrease the amplitude by c units. Oh, I don't know why I closed that. I just wanted to scroll down. So now what's happening is each value of y is going to get multiplied by 1 over 3 to shrink the graph. Multiply each value of y in f of x minus 2 by 1 over 3 to shrink the graph vertically. To make 1 over 3 times f of x minus 2. Then the last thing I'm going to do here is then I'm going to take that whole thing and I'm going to move it up by 5 units. Then I'm going to move 1 over 3 f of x minus 2 up 5 units. And then the last one that we're going to do, y equals f of 2x minus 1 Maybe I should do, let's not do A, let's do B. Looks more interesting. Y equals 2f of 1/2 x. So what happened to this thing first is I multiplied my x by 1/2, and then I multiplied that by 2, right? So you have to start from the very middle and then move your way out. So here I've got this, this activity on x. So I'm just going to remind myself, what is this horizontal shrinking or stretching? So C in this case is 1/2. Oops. C is 1/2. So C is between 0 and 1, which means I'm going to be stretching the graph horizontally by a factor of 1 over C. C is 1/2. 1 over 1/2 is 2. So I'm stretching it horizontally by a factor of 2. So now, oops. Multiply each x in f of x by 1 over 1/2, which is just 2. Technically, you got a fraction over a fraction, 1 over 1 times 1 over 2, or over 1 over 2 makes 2 over 1, or just 2. To stretch, oops, horizontally. And then I can stretch vertically, right, by 2 units. So now multiply each y value in f of 1/2, oops, by 2 to stretch vertically. That's it. So we need to be really good at just seeing these functions and kind of anticipating how they would behave. I encourage you to look at, even though I labeled it optional, right? Look at some of these functions and say, okay, well, my core function here would be root x. I know root x looks like this, and then I'm gonna shift all of that to the right by 4 units, right? Here I know core function is root x again. Root x again looks like this. I'm shifting it to the left by 4 units and then down by 3 units, right? Even something complicated like this, you can expand this out and you can say, okay, well, my x is squared, right? So my default function, my core function is x squared, but then I've subtracted 1 from my x, which means I have to move to the right by 1 unit. And then I multiplied it by -2, which means it's going to get flipped on the x-axis and then amplified by 2. So stretched by 2 and then +3, move it up by 3. Hard, but as long as you kind of start from the middle and work your way out, you can do something even like this last one here, which I would say is the hardest one. Any questions from you two? I haven't seen any else stop this recording, but if you have a question, let me know. Otherwise, have an awesome weekend, and I'll see you on Tuesday.
Thank you, you as well.
Yeah.